In this lesson, we're going to look at how temperature and pressure affect the solubility of solids and gases. Previously, we looked at a table that helped us to understand whether a compound was soluble or insoluble in water. We did not look at the limits of that solubility. Solubility of solids in water generally increases with temperature. Notice in the graph the x-axis is temperature and the y-axis is the amount of the solute that will dissolve in 100 grams of water. What we see is that these compounds increase in solubility as the temperature increases. The amount of increase varies. There are some compounds that are exceptions to this rule, but they are few and far between. The vast majority of solids will increase in solubility of water as the temperature increases. One example of this is in tea and dissolving sugar. If you try to dissolve sugar in iced tea, you're not going to find that much of it will dissolve. However, if you have a cup of hot tea, it is much easier to dissolve sugar in the hot tea because the solubility of sucrose increases with temperature. The solubility of gases in water decreases with increasing temperature. In this case, we see an opposite trend of what happens to solids. As we increase the temperature, we see that the solubility of a gas decreases in water. One place where this is relevant is in fishing. People who fish often go early in the morning or late at night when temperatures are cooler. When the temperature is cooler, more oxygen is dissolved in the water. Because fish have easier access to oxygen, they tend to be more active. When fish are more active, they're going to be more likely to look for food and more likely to come across the bait at the end of your line when temperatures are cooler. Although pressure does not affect the solubility of solids in water, it does affect the solubility of gases. And we see that the solubility of gas in water increases with pressure. So as we increase the pressure above a liquid, we will see that more of the gas particles will be forced into the solution and dissolve in the liquid. An example of this is a carbonated beverage. When you open a carbonated drink, you often hear the release of the excess gas in the bottle. When putting carbonated beverages in a bottle or a can, excess pressure is added to the container. This extra pressure forces more of the CO2 to be dissolved in the soda and keep it there until it gets to you and you drink it. Once you open the cap, you release some of the excess pressure and you will hear some of that extra gas escaping. If you drink the beverage in a short period of time, you will notice that the CO2 remains dissolved during that span. If the bottle sits on the counter and you come back to it the next day, you will find that the CO2 concentration is very low because the soda tastes flat, and that flat results from the lack of carbonation in the liquid.